Assalamu alaikum students. Today's lecture of which is part 2 of pressure sensors, and today we will start with C-Bourdon tube. The Bourdon tube works on a simple principle that a bent tube will change its shape when exposed to variations of internal and external pressure. It means when a tube is bended, its shape is changed when the pressure which is acting internally and externally on the tube is changed. So the tube also changed its shapes. As pressure is applied internally, the tube straightens and returns to its original form when the pressure is released. As we can see in the figure, it is in this form and called the Bourdon tube, and these pointers are used and calibrated as a for the measurement of pressures. And there are different advantages and disadvantages of C-Bourdon tubes. In some advantages, we can say it's an inexpensive uh, measuring instrument, wide operating range, has fast response, give readings as soon as possible, good sensitivity, direct pressure measurement, and some of its disadvantages we can say that primarily intended for indication only. It only indicates nonlinear transducer, hysteresis on cycling, and sensitive to temperature variations. We can say that it's sensitive to temperature variations. As temperature varies, the uh, tubes bending and straightening affects due to the change in the pressure ratings. A limited life when subject to shock and vibrations. Its life is decreases in different conditions. So next, helix and spiral tubes. It's also like the same thing. In helix and spiral tubes are fabricated from tubing into shapes as per their naming. As we can say, according to their name, these are there are different spirals of the tubes which are used. With one end is sealed, the pressure exerted on the tube causes the tube to straighten out as its one end is closed. So when the pressure is exerted on the tube, it started to straighten out, and its spirals are it started uncoiling and becoming straight, and its straightening or uncoiling is determined by the pressure applied, which is again we can say that the this scale is calibrated according to the pressure range of its coiling and straightening in positions, and it gives the reading of the pressure, and it has increased accuracy and sensitivity and high over range protection um, for usage, and it's uh, so very much expensive. So we can say that expensive because of its expensive rates, it has that disadvantage, and is not in the range of use of everybody is needs according to the needs of every person and students. And next, this is a spiral C-Bourdon tube. We can see these are the spiraled, and there when pressure one end is closed, one end is open, and pressure is applied at this end. And when pressure is applied, it's started straightening and measures the pressures of the applied liquids or gases. We can say whatever we want to measure. Spring and bellows. A bellows is an expandable element and is made up of series of folds which allow expansion, like we have seen in spirals and C-Bourdon tubes. One end of the bellows is fixed and the other moves in response to the applied pressure. Spring is used to oppose the applied force, and a linkage connects the end of the bellows to a pointer for indication. Like we can see that These are the this is the spring which is connected to the bellows and which shows the reading of the pressure which is applied. And this type of pressure measurement is primarily used for on-off control, providing clean contacts for opening and closing electrical circuits. This form of sensing responds to changes in pneumatic and hydraulic pressures. Uh, and here we can see that the force applied per unit area is equal to change in the pressure P2 minus P1. This is the formula where we can A is the diaphragm area in meter square, P1, P2 are the pressures in Newton per meter square. This is the spring and bellows uh, shows the two ends where there are different pressures are applied and we find out the value of the exact pressures. Differential pressure gauge, as it has two ends, both ends are connected to the line where we have to measure the pressure, and the difference between the pressure is shown at this scale in Pascal. Pressure per unit area, uh, square per pressure square in square per square inches, and these are the bellows which are connected to the spring and then gives the reading of the pressures. Pressure transducers and elements, electrical elements, we can say that the typical range of transducers are which are available is as shown here: strain gauge, vibrating wire, piezoelectric, capacitance, linear, variable differential transformers, and optical transducers. And there are different varieties of transducers which are available, which can be used in the measurement of the pressure and different quantities. And compression strain gauge, this is the diagram shown. Strain gauge patches are shown and tension strain gauges are shown in different values. Electrical pressure measurement elements, we say, and that several different technologies exist for the conversion of the fluid pressure into an electrical signal response. As we can say that these electrical elements use to convert the different fluid pressures into an electrical signal and then find out the different readings, and we can say these are also used to find electrical elements can also be used to measure the pressure, and different calibration techniques use the electrical signals. These technologies form the basis of electronic pressure transmitters, devices designed to measure fluid pressure and transmit that information via electrical signals such as the 4 to 20 milliampere analog standard signals. These are the different manufacturers of the, we can say, pressure sensor techniques, and which uses different principles like piezoresistive, strain gauge, differential capacitance, mechanical resonance, and by use different manufacturer companies and for them to construct or build the different pressure sensing techniques. Okay, in strain gauge, we can say that strain gauge sensing uses a metal wire or semiconductor chip to measure changes in pressure. A change in pressure causes a change in resistance. As the metal is deformed, this deformation is not permanent as the pressure applied force does not exceed the elastic limit of the metal. If elastic limit is exceeded, then the permanent deformation will occur. So here it is said that every metal has a limit, a range of which it of pressure which it can bear. So in case of strain gauge, that the they use the metal wire to sense the or semiconductor chips to measure the change in pressures. So when that change in pressure is within the given limit, then it gives a accurate reading. And when the pressure applied, or we can say the applied force exceeds the elastic limit, the metal does not come back to its normal shape, and its deformation occurs in that cases. This is commonly used in Wheatstone bridge arrangement where the change in pressure is detected as a change in measured voltage. As we have seen that the strain gauges works on the principle of that when a pressure changes, it causes a change in the resistance of the metal, and as metal deforms, so this change in resistance is also used in the Wheatstone bridges, and we may use this change in voltages to measure the pressure changes, and the scale is calibrated according to the change in resistance, which is directly proportional to the change in the value of the pressure. Strain gauge principle, we can say that the strain gauge principle, according to its R naught is equal to rho L naught over A naught, where R naught is actually a sample resistance, rho is sample sensitivity in ohm meters, L naught length in meter, and A naught is cross sectional area in meter square. Okay, by using these quantities, we can say that sample resistance, sample sensitivity, length in meters, cross-sectional area, voltage which is applied at one end of the Wheatstone bridge is equal to the product of cross-sectional area and length of the strain gauge, and which we can say that will be equal to the node length of the strain gauge plus change in length into area cross-section area of the strain gauge minus change in the area. So from these formulas, we can say we can find out the value of the uh, R, which is the resistance which is going to change as V is equal to IR, and by using these quantities and manipulating different formulas, we say that we conclude that change in resistance, which is will be equal to 2R naught into change in length over the length of the strain gauge. So we can say that the change in resistance is dependent upon the uh, sample resistance of the material and its change in length of the strain gauge, and it's the length of the given length of the gauge. And so by using these different values, we can find out the change in the resistance. Piezo resistive resistive sensor means that pressure sensitive resistance are a resistance that change value with the applied pressure. We can say which is also based on the principle of the strain gauge, and it changes its resistance according to the change in the value of the applied pressure, and it operates on the same principle which is used in the strain gauges. As we can see that the strain gauge is connected in between the Wheatstone ridge, and the excitation voltage is applied, and the change in the value of the resistance is measured by using this Wheatstone ridge. We And there are different advantages and different disadvantages of strain gauges. And if we just take the advantages of strain gauge, it has wide range of pressure measurement. So we can say that from 7.5 kilopascal to 1400 megapascal, and very low inaccuracy of about 0.1%, and it's also small in size, stable devices with fast response, and most of these have no moving parts, good overrange capability. And few of its disadvantages, you can say that unstable due to bonding material, and it's temperature sensitive, and also thermoelastic strain cause hysteresis problems in the devices. A piezoelectric, we can say when pressure is applied to crystals, they are elastically deformed. For the case of the, we can say crystals. Piezoelectric pressure sensing involves the measurement of such deformation. When a crystal is deformed, an electric charge is generated for only a few seconds. The electrical signal is proportional to the applied force. So we can say that when we will apply a pressure or force at any crystal material, that it will it will be deformed, And piezoelectric pressure sensing involves the measurement of such deformation. Because of this deformation, when crystals deform, an electric charge is generated only for a few seconds, and from those few seconds, an electrical signal is we can say that is generated, which is proportional to the applied force which causes the deformation in the crystals. Quartz is commonly used as a sensing crystal as it is inexpensive, stable, and insensitive to temperature variance. Tourmaline is an alternative which gives faster response speeds, typically in the order of microseconds. So we can say that quartz and tourmaline are two commonly used materials which are used in piezoelectric pressure sensing devices. According to the, we can say the advantages of piezoelectric sensing devices, their accuracy is about 0.075%, very high pressure measurement up to 70 megapascals, and they are also in small in size and they give robust response, fast response, we can say even less than 1 nanosecond, self-generated signals, and their disadvantages have dynamic sensing only and temperature sensing. As we can see that almost up till now, most of the sensors are all mostly sensitive to the temperature changes. Capacitance, we can say that for capacitive pressure measurement involves sensing the change in the capacitance that results from the movement of a diaphragm. The sensor is energized electrically with a high frequency oscillator. This type of pressure measurement is quite accurate and has a wide operating range. Capacitive pressure measurement is also quite common for determining the level in a tank or vessel, and different deep, uh, we can say storing tanks, we can measure the levels and pressures and different quantities by using the techniques of capacitance measurement. Differential capacitance sensors had, we can say, another common electrical pressure sensor design works on the principle of differential capacitance. As we can say that the change in capacitance is measured and calibrated, change in the capacitance is calibrated according to the change in the capacitance. In this design, the sensing element is a metal diaphragm located equidistant between two stationary metal surfaces, forming a complementary pair of capacitances. An electrically insulating fill fluid, usually a liquid silicon compound, transfers motion from the isolating diaphragm to the sensing diaphragm and also doubles as an effective dielectric for the two capacitors. And by using these different, we can see that there are two sides on which the pressure is applied, and by this application of the pressure, that these sensing diaphragms are compressed and depressed, and by using this the output terminals are connected, and this and there these change in the sensing diaphragm, we can say from the transfer of motion, we find out the value of the pressures. Differential capacitance sensor, Rosemount models are we can see here, and there are Rosemount models that there are 2 points where the pressure is applied, and then the difference of the change in capacitance are calibrated to measure the value of the pressure. These are some figures of live working differential capacitance sensors which are used in the industries, and their internal circuit diagrams are internal circuitry, and their components are shown. Electronic PCB boards are used, isolating diaphragms are shown, and differential capacitance sensor is connected inside the sensors. Differential pressure transmitters, one of the most common and most useful pressure measuring instrument in industry, is the differential pressure transmitter. This device senses the differences in pressure between two ports and outputs and generated a signal at the output point representing that pressure in relation to a calibrated range. Differential pressure transmitters may be based on any of the previously discussed pressure sensing technologies. So this section focuses on the applications rather than the theories. In that in which condition and in which environment and what are the applications of these transmitters which transmit the differential pressures. Electronic differential pressure transmitter. As shown here, there are two wires connected electronically diaphragm capsule assembly, which high and lower end pressures are measured. Two models of electronic differential pressure transmitter appear in the this we can see there in the figure. It has two sides of the applied pressure, and then the electrical signal is generated and which is calibrated according to the change in the pressure of the electric differential pressure transmitters. These are also two more diagrams of electronic differential pressure transistors in the photo, and this is from the Yokogawa and at the left and Foxborough on the right side. This is the we can say the concept of differential pressure instrument. Port labeling is very similar to the inverting and non-inverting amplifiers labels apply to the operation amplifier input terminal. You can say inverting, non-inverting, and these are high pressure and low pressure. And diaphragm flexes to the right as high pressure is applied. Signal is generated, which is converted to the amount of the pressure which is applied. When both sides have equal pressure, then we can see that the diaphragm is straight instead of the flexes to the though there are no flexes. And when pressure high pressure side has is, is lower than the low pressure side, then the diaphragm flexes to the left and signal decreases. And in this case, we can see that signal has increased, and we can use this as a inverting and non-inverting amplifiers application. And this is their generation of signals that that is in terms of currents, 4 to 20 milliampere current and the compressed air, and this is the internal circuitry and working principle of the differential pressure, electronic differential pressures devices. Again, air compressed air pressures are used here, and different techniques applied voltages are shown. Pressure sensor accessories, we can say that multiple accessories exist for pressure sensing devices to function optimally in challenging process environments. And these accessories we say that are necessary to be there and used for different purposes. Sometimes we must use special accessories to protect pressure instrument against hazards of certain process fluids. One such hazard is pressure pulsation, for example, at the discharge of a piston type positive displacement, high pressure pump, and pulsating pressure can quickly damage mechanical sensors such as Bourdon tubes either by wear of the mechanism, transferring pressure element motion to an indicating needle, and or fatigue of the metal element itself. That high pressures can damage the different elements. So different accessories are sensor accessories are required to handle these tough conditions. Next time, inshallah, we will look for the valve manifolds and what are that important, which is an important accessory to the differential pressure transmitters. Um, and it's a, and also we'll see that valve manifolds, which are works and their principles and their applications. Okay, students, take care. Allah Hafiz. Assalamu alaikum.